Now I want to speak about modular addition and multiplication. So how could I add modulo 6? For example, modulo 6. If I want to add 3 plus 7, well, it's the same as 10, but 10 modulo 6 is the same thing as 4. And if I want to multiply, so 3 times 7 is the same thing as 21, but this is the same thing as 15, for example, or as 3 modulo 6. Now this is confusing, saying 10 equals 4 and 21 equals 3. Yeah, because I have to say all the time modulo 6. Modulo 6. That's how it works. But sometimes we are still not happy with that notation, because we would say this number is 10, and I'm saying 10 equals 4. But in the natural numbers, 10 is not equal to 4. So those are not really the natural numbers I'm speaking about. Yeah, it's true. I'm not speaking really about the natural numbers. I'm speaking about the natural numbers, modulo 6. And sometimes we want to make the distinction between the natural numbers which live on this line and go to infinity, and those numbers, modulo 6, which live on a circle and wrap up each time and go back to where they started. And to do this distinction, often for the sum and multiplication, or for anything, we use the notation with the bar. So we say, instead of saying 3 plus 7 equals 4, modulo 6, I say modulo 6, of course, 3 bar plus 7 bar is 4 bar. And this way I eliminate the confusion between the natural number 4 and 4 modulo 6. And even the plus here is not the plus of natural numbers. This is the plus of numbers modulo 6, so I give it a new name, plus bar. And the same thing for the multiplication. I can write 3 bar times bar 7 bar equals, I can write 21 bar, but 21 bar, as I said before, the class of 21 is the same thing as that of 3, because 21 divided by 6 gives a remainder of 3. Now what is 0 bar times 4 bar, let's say? This is the same thing as 0 times 4 bar, and which is 0 bar. This is in fact how I define the sum. So I'll write the definition here. Sum modulo n. So if I have two classes, modulo n, a bar and b bar, so the sum I denote by plus bar, and then I write a bar plus by b bar is the same thing as a plus b bar. As if I were doing the operations on those classes, on those sets, rather than on the numbers, but it's just the same thing. The advantage is that it eliminates some confusion between the natural number as a natural number and the natural number modulo n. And the same for the multiplication. A bar times bar b bar, the same thing as a times b bar. And here I have to say the plus here is the plus of natural numbers, the multiplication here is the multiplication of natural numbers, and these plus bars and multiplication bar are those operations I am trying to define on those classes, or addition and multiplication modulo n. Now I can give a definition, fix n a natural number, and I say that a in z is invertible modulo n if and only if there exists a b in z such that a times b equals 1 modulo n. Or equivalently in the better notation, a bar times bar b bar equals 1 bar mod n, which is equivalent as saying that a times b is congruent to 1 modulo n, or a times b minus 1 is divisible by n, or when I divide a times b by n, I have a remainder 1. All those things are just saying the same thing in different ways. So let's give an example to understand this definition. So say modulo 12. I ask, for example, is 5 invertible modulo 12? So we want to find a number x, natural number, or just an integer, such that 5 times x is the same as 1 modulo 12. Does this exist? So stop the video a little bit and think about it. Well, what I will do, I'll try the x's. I'll try, first of all, 5 times 0 is the same as 0 modulo 12. And 0 is not 1 modulo 12. Now 5 times 1 is the same as 5, which is distant from 1 modulo 12. 5 times 2 is 10. 5 times 3 is 15, which modulo 12 is 3. Modulo 12 I can write as well this way, with brackets. Okay, 5 times 4 is 20, and 20 falls in the class of 8 modulo 12. 20 divided by 12 gives remainder 8. 5 times 5, this is 25, and this is the same thing as 1 modulo 12. So the answer is yes. 5 is the inverse of itself. Another example, like modulo 12, exercise, is 7 invertible. And what's its inverse, if it exists? So when you try them, 7 times 1, 7 times 2, etc., you reach, in fact, 7 times 7, which is 49, which is 48 plus 1, and 48 is 4 times 12 plus 1, and this is equal to 1 modulo 12. And so the answer is yes, and the inverse is 7. And it's not always the case, of course, that the inverse of the number is the number itself, or that an element is always invertible. For example, 2 is not invertible modulo 12. Why? If it were so, then I should find some a in Z such that 2 times a equal 1 modulo 12, which means that 2 times a minus 1 is a multiple of 12, is something of the form 12k, which means that 2 times a minus 12 times k is 1. And this is a contradiction, because this thing here is divisible by 2. It's an even number. And the 1 is not divisible by 2. So this is a contradiction. Now, an important question is, when is the number invertible modulo n? And how do I calculate the inverse? As we saw in the examples, we just guessed and tried numbers to find the inverses of 5 and 7. But in general, we cannot guess and try, because in the applications, the numbers which appear are so huge that you cannot guess and try. In cryptography, as I already said several times, you have numbers of the order 10 to the 600, like numbers with 600 digits. And you want to inverse another numbers of hundreds of digits as well. So you cannot guess and try. You want an efficient way to do it. And the way we do it is using the Euclidean algorithm. And this will be the object of the next video.